Okay, so I'm going to give industrial perspective. I'm giving industrial perspective. I'm a fellow of Rolls-Royce in computational sciences. I've just passed my 32nd anniversary of working for Rolls-Royce. I spent much of my career doing computational fluid dynamics and I've transitioned into computational sciences. I'm going to start as I always do with a bit of a business overview, just so everyone's clear on what I'm going to talk about. It's not cars. So this is Rolls-Royce. We have three business sectors: civil aerospace, defence and power systems. I'm not going to go through all the numbers, you can see them all up there. So civil aerospace is about about half of the business, twice the size of the other two. Much of my work's been done in civil aerospace. I have worked in some other areas. We have HPC across all of those sectors, but again, the largest installations are in civil aerospace. And then the other one just looking out, in terms of our R&D activity, we spent last year £1.4 billion in use of R&D, and about 1.1 billion of that was Rolls-Royce's own money. And a lot of our own money on R&D. Just one other slide then on the business. These will be common themes across many industries. So three main drivers for the business. One is the green agenda, cleaner, safer power, and as part of that, electrification. So just as the automotive industry is moving towards electrification, so are we. We've got several activities on that. We've got one in particular with a company down in Gloucester, and we're hoping to break the airspeed record soon for all electric flight. We're doing quite a lot on electrification. And then digitalisation of the business. And for those of us that's been in HPC, we've been digitalising our business for the last 30 years. So I'm sure others feel the same about digitalisation. So in terms of modelling and simulation, I think you saw this picture yesterday. So this is gas turbine engine, and we just saw a couple of pictures in the previous slide. Just some stats on that. First one, the fan at the front, that will empty the air out of a squash court in less than a second. The air going in there is about 350 miles an hour. We compress the air to about a 50th of its size before it goes into the combustor. That combustor burns at 2000 degrees C. The metal melts at about 1300 degrees C. As you go through, so there's the combustor. That's the combustor. As you go into the turbine, turbine blades are about that big, and each one of those generates the same horsepower as a Formula One car. And again, the air temperature there is 200 or 300 degrees above the metal temperature, the melting point of the metal temperature. As it comes out the back, it's going at 900 miles an hour. And then my favourite stat is one of the ways that we stop the metal from melting is we have coatings on the blades, so thermal barrier coatings. These are sub-millimetre coatings, and they can withstand a 200 degree temperature difference across them. So if you got an ice cube and coated it in our thermal barrier coating and put it in your oven at 200 degrees C, it would never melt, in theory. So yeah, we all have difficult problems. We like to think we make the most complex product on the planet. I'm sure others could lay claim to that as well. So that's the backdrop. Those are the sort of things that we're modelling. In terms of drivers, three drivers I'm going to talk about. We've touched on them already, I think, to some extent. So the first is complexity, component complexity. So let me just explain what we've got here. Is there a pointer or something? No. No. Doesn't matter.
No, it's not.
Okay. So if you look at the top one, what you've got, the vertical line. Let me. My mouse will do it now. Oh yes. So what we're looking at a blade from the side on. So that is the. Oops, where's my mouse gone? So that's the leading edge of the blade. Air is coming in from the left, flowing towards the right, and what we have. As the air comes in from the right, it grows a boundary layer on this bottom wall. So this is what we would call an end wall. That boundary layer grows as it comes in. It then interacts with the boundary layer that's growing on the blade. And that interaction creates a vortex, corner vortex, that then grows as it goes through the blade. And then when it comes off the back of the blade, it grows into a much larger vortex. That top one, that's an idealized model. That's what we would do maybe 10 years ago. Very idealized. In reality,
There's lots of different geometry features all around. So in particular, we have these cavities. And those cavities, some of them are part of our cooling mechanism. So flow will be leaking out of those. So cold flow will come out of those cavities. And that, as you can see, that flow that comes out of the cavity there, that flow that, oh, I can reach this one. That flow that comes out of the cavity here disturbs this boundary layer. Therefore, you get a much bigger corner vortex and a much bigger effect downstream. And if we look at that in terms of measurements, so this is CFD predictions versus the experiment. With the approximate model down here, we're some way away from the data. As we start to put in the proper geometry, then we get much closer to the data. That's just a line of computed versus measured. One of the messages from this is high fidelity simulations isn't just about physics. It's about making everything high fidelity. You need better geometry, and by having better geometry, you therefore need generally better meshes. And the meshing for some of these very complicated geometries is much more difficult than an aerofoil. So you tend to get much lower quality meshes in there. So meshing is difficult. Obviously, we've now got, there's much more complicated physics going on here. So we might just use a normal turbulence model up there, large eddy simulation down here. So physics, and then because you've got these very high condition numbers, because you've got poor mesh, you need better linear algebra, better matrix inversions, and of course then that all leads to a bigger problem, and you need better computers to run that. So that's one driver towards complexity. You've then got component interactions, and turbines, turbine engines do what they do by having alternating rows of stators and rotors. So there's many of these through the machine, and basically you've got a dynamic topology. One rotor is moving past the next. At the moment, the topology within a domain is fixed, but it is moving. So every time you do a time step, you've got to reconnect your topology, reinterpolate across that boundary, and then move on to the time step. And as you can see from the picture at the top, those are speed ups, or sorry, runtime. So we get some scalability. It scales similarly to the steady code down to about 2,000 cores. I think that was 1920. But then as you go further, you lose the scaling. It actually gets slower as you add more cores. Those results are a couple of years old. We have improved on those since then. And then once you can do the component coupling, then you can start to do system modelings. And really it's being able to do systems is the other big driver for the calculations. First reason for doing that is you can move your boundary conditions away. So you can have boundary conditions at the start and the end. When you do a component, your boundary conditions have got to come from somewhere. You can't do a calculation without boundary conditions. So they often come from a lower order model. We'll do maybe an axisymmetric or a 2D model to generate boundary conditions for a single component. Once we can do a whole subsystem, we then have boundary conditions just at the inlet and entry. And also, you've got all of the components potentially interact with each other. So in this case, the blade at the back, the blade at the front. Lost my mouse again. The blade at the front can influence the blade at the back, and vice versa. So you get pressure waves. We saw the acoustics in the last slide. You can get acoustic waves, pressure waves that come forward from the rear blade that influence the front one, and you get normal convection, vortices, boundary layers, wakes, etc., that then flow downstream and affect the front ones, affect the back one. And again, if you want to do that and get good answers, there's a driver to do better physics. So you can't really do that with a steady state. So these calculations here, you've got pressure rise, which is the measure of how well you're compressing the air, and then you've got efficiency as to how efficient you are at doing that. One of the key things in designing compressors is what's called the stall point, the operability of the compressor. I'm sure when you've flown, you've all been flowing and felt the wing install, you're flying, and all of a sudden the airplane drops. That's a sort of mini stall on the wing. We have exactly the same inside the machine. So this stall point is an important design characteristic. What happens here is the steady state calculation can only get that far. the steady state will diverge at that point. If you run unsteadily, it's not perfect, but it's definitely better. We definitely get a much better prediction of that stall boundary. So what does that mean for us as a business? Why do we do all this stuff? So this is the XWB and a new engine. I'm not going to read all of these off, but as you go around the machine, look at the different components, we're using simulation of one form or another. A lot of CFD, a lot of finite element analysis, a lot of thermal analysis, etc. And things like weight. We do the stress analysis so we can reduce the weight, etc. These are stats from our website. So that's stats of 6 times the computing power applied than the previous generation. I don't know where that comes from, but it just feels too low to me. It feels far too low to me to be correct. So I'm not going to go through all of those. I'm just going to pick on one area where we do simulation on that. So pick on the fan. We actually do a lot of different types of simulation on the fan. Basic aerodynamic performance is important. The acoustics that we've just seen is also important. We have various criteria. One of the criteria is if a fan blade comes off, it has to be contained within the engine. So there are, the containment around here includes Kevlar and various features that are there to contain the engine, and there's an interaction between the shape of the fan and the containment system. So if you can see here, you see the fan there is arced forward. That improves aerodynamic performance, but because the line of sight of that leading edge of the blade could potentially come outside the blade, we've got to move the containment system forward so we can contain that bit of blade if it comes off. Therefore, you add weight, and so we have all of these compromises between improving the aerodynamics in one place and maybe making it noisy or making it heavier, something. So one of the simulations that we do, there are a number of simulations that are mandated by the FAA and the EASA and the Civil Aviation Authority, one of which is Birdstrike. And I'd say this, that for some non-Darwinian reason, birds like to flock at the end of runways. And on civil aircraft, there's about 25 bird strikes a day. And there's a range of things that we have to do. So we have to simulate flocks of birds, and we have to simulate a range of heavier birds. If you go on YouTube, you can find some nice movies about some of these tests. The tests that we actually do, we will fire, they're dead before we fire them, but we fire the birds. we fire the birds at the engine. And there's always this apocryphal story of somebody forgot to defrost the bird before they fired it at the engine. I'm not sure that's true. But we do simulate this, and this is an interesting one because this is an area where we've actually convinced the aviation authorities that we can certify by analysis. And obviously one of the directions of travel of all of this, and I guess for many of us, is that we want to do more simulation and get our products certified via simulation rather than via testing. Testing is expensive. So what we do, this is a test that we would perform. I'm not quite sure the number in here. So this is the simulation here, and this is the test here. So you can see this is the main impact point here, and then we tend to get this trailing edge, what we call trailing blade damage. So in this view, the blades are rotating anti-clockwise. So the main strike is here, and then these other blades come around and also make a strike. It must bounce or something, which is why the next one's got no damage. It's not my area. I'm not an impact person. So it's pretty good, And as I say, we've based on and it probably took us, of the order of 10 years to go from being able to having the capability to do these type of simulations to convincing the CAA that we could certify rather than do the test. Took us about 10 years of evidence building and creating the confidence that we could do that. So bottom line, at a business point of view, how does simulation and HPC affect the bottom line? You can see there's two I'm just going to pick out. One is the fuel consumption. So the Trent XWB, in terms of the engine that it replaces, it's about a 15% improvement in fuel consumption. And what that means in our money, in pounds and pence in the UK, dollars and cents in the US, it's about a $2.9 million saving per year per aircraft for the airline operators. Okay, high performance computing, the reason we're here. I think Mark Parsons alluded to this model yesterday. He didn't show this slide. We've had this slide and used it for 3 or 4 years now. What the basic model is, we as a business can look into the future. We know what the market drivers are, we know what the legal drivers are, and increasingly we know what the sort of societal drivers are. You know, somebody was talking about flying supersonic across land. So we can see into the future what we believe to be the business requirements, and therefore what products that we're going to have to be able to design in the future. So the sort of production systems that we're going to have as proven capabilities 3 to 5 years from now. And often, if we then work back today, it's really hard to build those test cases. So building them, you know, where today we might build models of 100 million cells, if we want to build a model that's 1 trillion cells, actually that's really hard today. So we have these breakthrough cases. And so I sit here, so I used to sit here in physical sciences, sitting there here in computational sciences. And part of the model is, unless you can run your code in a reasonable amount of time, you can't really do the physics. You know, if it takes you 3 months to run your code, that pretty much limits how quickly you can advance your physics. So, you know, scaling the codes, getting them to run large models, being able to do all of the complexities of the geometry. There's a lot of computational science in there. I say some of it's just straight linear algebra. There's a lot of scaling, and then once we can scale codes and run them in a reasonable amount of time, we can then start to do the sort of physical science, the physical research and innovation. And from then, we can then go on to the design innovation. And once we trust the codes, we can then model different types of configurations and different design choices. And so that's a slide that we've used regularly. Oops, wrong way. So this is that model in action. So this is Archer. There are deliberately no scales on here, so do not ask me what our in-house capability is, because I'm not going to tell you. But it's you know, as a cartoon level, it's correct. So we started working with Mark, with EPSRC, with Susan Morell, that many people will know, and then around about the 2014 mark, to give you an idea of the time scale, we had a pilot activity on Archer. Supported by Mark. That sort of led to what was called the leadership scheme, which was a sort of quote insight, a mini scale down insight type activity. Mark mentioned insight yesterday. And overall in that period, we had about 18 to 24 months of time on Archer where we could do pre-competitive code scaling. There's a picture up there. Some of you all know Rota 37. It's a well-known public domain test case. In terms of scaling studies, we tend to stop when we get to 50% scaling. So we managed to scale that to sort of 34,000 cores, which until a couple of weeks ago was our biggest run. We've now done 55,000 cores on Archer. And the fundamental thing is we couldn't have done that on our in-house systems at the time for 2 reasons. One, the in-house system wasn't big enough, and two, the in-house system's there to do production design. We wouldn't have been able to kick off all of the designers designing the next engine to do our research and innovation runs. But the point we make, and there's an economic argument coming, when we then upgraded, and actually in this period there were 2 upgrades, so this was the second of our upgrades in that period. That system, those codes, were used almost from day one on that system. And anyone that scales code, the person that did this, Matt Street, who used to work for me, he calls it whack-a-mole. You just fix one problem, then the next one, and the next one, and you keep going until you get it scaling. And every so often you get an integer star 8 issue, a 32-bit integer, and you go away and code in some 64-bit integers and so on to get it to scale. And the argument that we make is, so Archer 2 is probably the main figure. I forget the exact number. It's about £70 million investment. Archer 2, government's announced that. Industries like Rolls-Royce are not going to spend £75 million on a new computer. But the argument here is when we did upgrade, broadly speaking, it was half the price for twice the speed. So in that period when we did all of the pre-competitive scaling work, the economics of deflation, etc., on computers then worked in the industry's favour, and so we were able to buy a better system. The other, perhaps the more important and more significant one, is that then led on to the EPSERT Prosperity Partnership that we're going to talk about. And if it weren't for this pre-competitive access, we wouldn't have been able to do that. We wouldn't have built up the confidence that we could do the computer science. And this is all about software engineering, computer science, and that's, as we've all said, that's where the value of our activity lies. And it's the same model again. Archer 2 will again be significantly faster than our in-house capabilities, and we'll just do the same model again. This is just a quick snapshot of something we've done. Since putting this together, I think we've now actually run a 4 billion simulation. So again, we're pushing. This is allowing us to push the boundaries of the types of simulation that we're doing. It's just a bit of a cartoon picture. I'm not going to talk through the picture necessarily. Then to finalise the future directions, we've touched on this. So this is our prosperity partnership, which we call ASIMOV, is the name for it. I forget what ASIMOV stands for. Advanced Simulation and Modelling of Virtual Systems. That's it. Yeah, it is an acronym, but none of us can remember what it is. It's an interesting one in the Rolls-Royce. We do a lot of work with universities, and we have this university technology centre type structure where we will work specifically with universities for the long term. So our first UTCs started in the early 1990s and are coming up for their 30-year anniversary. This is unique in that portfolio. We have about 30 UTCs. Most are in the UK, but some in mainland Europe, some in Germany, some in the Far East. So and it brings together the physics and the computers. So as you can see there, we're trying to drive it with grand challenges. So our objective is a complete simulation of a gas turbine in operation. So from a computer science point of view, several orders of magnitude improvement in computational performance. We're only going to be able to, and we believe we'll need an exascale computer to do this. So we're only going to get there if we can improve the computational performance. And again, from the whoosh chart I showed earlier, once we can do that, we can then start to model things that we can't model today. And from that, we will get new science and novel designs. So we launched, this is just about past our first anniversary. It's a 5-year program. I'm the business principal investigator. Mark's the principal academic investor. Then we've got Bristol, Cambridge, Oxford and Warwick as other universities, and then 2 SMEs, CFMS, Zentech, and we've got support from Intel, ARM, Microsoft and NCSA. 2 slides to go. This is really back on the message around scale. And once you go unsteady and you want to do a complete turbine, all of a sudden you're going up 50,000 times in the amount of compute power you need. I think we saw this one yesterday as well. So this is a little bit finger in the wind, but we've scaled up the mesh sizes that we use today. So we do believe it's going to be 1 trillion cells, probably maybe even 10 trillion. 1 billion core errors per calculation, and when we put this together, the prevailing cost of a core error was 10p. So I'm not sure we'll ever spend £100 million doing one calculation. So and that sort of leads on. Last one. This is the last slide. That sort of leads on to the strategic themes of the program. So extreme computing, we've seen that a lot. People know that. Cost of computing is also really important. We're a business, we've got to justify every pound we spend almost. So lean computing, both in terms of asset utilisation and engineer utilisation, as we potentially move to quite a complicated ecosystem of external high-performance computing, in-house high-performance computing on the desktop, in the cloud, productivity, queuing, etc. Trusted computing, there's a security aspect in there about security of aspect of our data, but also trust in the solutions. We can do these huge calculations, and we might be cancelling a test as a result of that. We've got to be confident we're getting the right answer. And then computing platforms, and we saw that earlier, as trying to be agnostic of computer platforms. So we deliberately separate computing platforms from extreme computing. Thank you.